Hello, everybody. This is the 10th and the last lecture from the first part of our course, Fundamental Physics, in which I will introduce you to the band theory of solids. I will give you physical and mathematical reasons why quantum states of electrons in periodic crystals split into clusters of quantum states which form bands. I will tell you how band filling is related to electrical conductivity of a material. I will explain why there are dielectrics that do not conduct electricity, how they differ from semiconductors, why some materials do conduct electricity, namely metals and semi-metals. So these are the four main conduction types of crystalline solids. Then we will discuss the difference between the direct and indirect bandgap semiconductors, and I will introduce electrons twin brothers, which exist in semiconductors and which are called holes. Maybe this would be not twin brothers, but antipodes, holes, positive charge carriers, that play just as important, whose role in semiconductors is just as important as the role of electrons. So let us begin. From the crystallography part of the course, you already know that crystal structure is defined by the Bravais lattice and the basis that is attached to each lattice point of the Bravais lattice. Let us assume for now that the basis of the crystal is a single atom. Yeah. There are plenty of crystals where the basis is a single atom. Let us focus on a single atom. I do not know, copper, for example, FCC lattice. A focus on a single atom in the absence of all other 10 to the power 25th or so atoms of the crystal. Now, electrons in an atom form orbitals that form in turn energy shells, okay, L10 and so forth. So in a given orbital is defined by the orbital quantum number L and the magnetic quantum number M. Each orbital can accommodate two electrons of opposite spins, up and down. Now imagine what happens if you bring those atoms together so that the electron wave functions start to overlap. So in two atoms, that as they come close together, the wave functions of the electrons that belong to the same orbital start to overlap. Now that orbital would have two electrons. Let's say this is a valence electron, and the orbital had just one electron. So okay, now the orbital has two electrons, but actually there are more than two atoms in a crystal. There is an astronomically huge number of atoms, 10 to the power 25th or so. So what? That orbital would have to accommodate 10 to the 25th electrons. No, this is impossible because of the Pauli exclusion principle. By Pauli exclusion principle, a single orbital can accommodate at most two electrons. So what do those orbitals have to do to accommodate this huge 10 to the power 25th number of electrons? Well, they have no other choice but to split into clusters of closely spaced on the energy scale states, and those clusters are called energy bands. So this is the physical reason why energy bands in crystalline solids appear. Now, what if the basis of your crystal lattice is not a single atom? What if it is two or three, I do not know, arbitrary number of atoms, but it is not very big. It isn't, yeah. Well, in that case, you can treat a group of atoms that forms a basis of a particular unit cell of the crystal, or the primitive cell of the crystal, I should say. you treat the atoms that form the basis of a primitive cell as a molecule, but it is not a real molecule. It is a molecule in quotation marks, a quasi-molecule. Not a molecule, but something that can be treated as a molecule, only conceptually. That is, you place the nuclei of those atoms in exact same positions as prescribed by the vectors of the basis. And you consider this as a cluster of molecules, as a cluster of atoms. And you can solve Schrödinger's equation, at least in theory. You can solve Schrödinger's equation for an electron in such a cluster of atoms in the absence of all other 10 to the power 25th primitive cells of the crystal. So you just imagine you place the nuclei in specific positions according to the basis, and you treat this as a molecule, and those atoms produce some potential, and you solve Schrödinger's equation. Again, you will get orbitals. Now, maybe those orbitals will be classified according to some own set of quantum numbers, but you get some orbitals, and now you bring all those quasi-molecules or clusters of basis atoms together. You imagine you're reducing the lattice constant. So initially, let's say you pretend that the crystal has a very large lattice constant, but preserves the same symmetry. Like if it is FCC symmetry, then you just separate the atoms by a large distance. You increase the lattice constant, but preserve the FCC crystal structure. Initially, your lattice constant is so big that the clusters of atoms, basis atoms, do not interact with each other. The wave functions of the electrons do not overlap. And then you have those electrons occupy some quantum states, orbitals, with well-defined energies. So at large distances, at large interatomic distances, those energies have well-defined values. And then again, as you bring those clusters together by reducing the lattice constant, those quantum states have to split into bands. So nothing changed if you had, in comparison to the case when the basis was monatomic, a single atom. So splitting of those quantum states into bands is a natural consequence of Pauli's exclusion principle. Now, how many bands should we have? Well, that depends on the number of quantum. That depends on the number of orbitals. Each orbital splits into a band. If orbitals had similar energies, then the bands into which they split they can overlap. Yeah, they will overlap in bands, or they can repel each other. They can hybridize, just as in the sp3 hybridization process that we have discussed when we talked about formation of diamond crystal lattice, silicon, carbon, diamond. But there will be bands. Now, the number of bands into which each orbital splits is exactly the same. The number, not of bands, the number of quantum states in each band would be exactly the same as the number of primitive cells in the crystal. The number of quantum states per band is the number of primitive cells in the crystal. And each quantum state within the same band can take in at most 2 electrons. So each band can accommodate at most twice the number of primitive cells, electrons. Okay, so that was the physical reason why bands are formed. Now let's talk about, no, not quite. We are not quite done yet. So some terminology. Quantum states in a band are characterized by the wave vector. So here is the thing. Electrons in a crystal do not belong to particular atoms. The wave functions, as long as the wave functions of electrons start to overlap, each electron now becomes the property of the whole crystal. It is shared by the whole crystal, by all atoms. In other words, electrons become delocalized. And since they become delocalized, this is something like having a plane wave. We know that a plane wave is a delocalized object. So electrons in bands, their wave functions have the structure of a plane wave. It is a little bit more complicated. I will talk about the structure of this wave function a little in the next slide, but it is similar to a plane wave, and it can be characterized by the wave vector. Now, the energy of each quantum state within each band will depend on the wave vector, just like the energy of a free electron depends on the energy of a free electron is proportional to the wave vector squared. Because the wave vector is related to momentum, kinetic energy is momentum squared divided by twice the mass. So the kinetic energy of a free electron is proportional to the magnitude of its momentum squared. Now, in crystals, things are a little bit more complicated because different crystallographic directions, they are slightly different. They differ from each other, right? So it can be expected that the energy of an electron will depend differently on the magnitude of the wave number, of the wave vector, the wave number, for different crystallographic orientations. And so here are the energies in five bands of silicon. Notice as on the y-axis versus the wave number or the wave vector measured along different crystallographic orientations. So the right part of this graph shows energy versus wave vector for the orientation 1, 0, 0, and of course by extension 0, 1, 0, 0, 0, 1, negative 1, 0, 0, and so forth. The left part is measured along the 1, 1, 1 crystallographic orientation. Notice that the wave vector dependence of energy is no longer a quadratic function. So we can have a maximum even at some non-zero for this band. Also notice that some bands overlap, like these two bands and these three bands, and that's exactly because the electron quantum states of silicon, of free silicon that later split into these bands, overlapping bands, those electron quantum states, orbitals had similar energies or overlapping energies. So what else? Yes. Here we also observe that some bands are separated by an energy interval, which is called the band gap. And within the crystal, electrons cannot have energies inside the band gap. So it is either this band, one of the bands, or this band, but nothing in between. And I should immediately make a statement that this is not true if the semiconductor is doped. So if you deliberately introduce impurities into the semiconductor, then electrons can have energies inside the band gap, but those are electrons that are bound to the impurity atoms. So this is possible. But in a pure semiconductor crystal with perfect crystallinity, electrons cannot have energies inside the band gap. All right, but we will talk about doping later in a few lectures. Now let us discuss the mathematical reason. So far we have been talking about the physical, the qualitative reason why electrons have electron states split into bands. Now mathematical reason. Mathematical reason is offered by Bloch's theorem. It was it was proven by Felix Bloch, a Swiss physicist, in 1929. But in mathematics, this theorem has been proven much earlier by a French mathematician Floquet. His name is Floquet, so it has been known to mathematicians for about 40 years. So anyway, Bloch's theorem. But of course, mathematicians didn't apply it to crystals, specifically to electrons in crystals. So I'm not trying to say that to diminish Felix Bloch's contribution. It was a great contribution. All right, okay, so we have a crystal. Each electron in a crystal finds itself in a periodic potential. That potential is generated by the positive ions that form the crystal lattice, that are in the nodes of the crystal lattice sitting, and other electrons. So let's say the crystal has 10 to the power, I do not know, 27th electrons. So, and you are focusing on just one electron. All the remaining electrons produce some sort of mean field potential. And even though it is not a trivial task to figure out what that mean field potential is, for our purposes, it is enough to say that this potential exists and that it is periodic and it has the periodicity of the crystal lattice. All right, so each electron finds itself in this effective potential which has the periodicity of the crystal lattice. That means that if you replace the argument R, position R, of that potential by any lattice translation vector, the potential will repeat itself. You will recover the original value of the potential. And let's say we are trying to solve the time-independent Schrödinger's equation for an electron in this periodic potential. Without performing any calculations, we can say the following. The wave function of the electron will not have the periodicity of the crystal lattice. It will not. Because the wave function itself cannot be measured. The phase of the wave function cannot be measured. But the observable, the measurable quantity associated with the wave function, the probability density to find an electron at a particular point, which is the modulus squared of the wave function, must have the periodicity of the crystal lattice. So if you replace the position R with R plus any translation vector D, then the modulus squared of the wave function will not change. Okay, this is one statement that we can make about those solutions of the time-independent Schrödinger's equation. The modulus squared of the wave function has the periodicity of the crystal lattice. The second statement that we can make is that in a particular special case, when there is no periodic potential, so you set the periodic potential to 0, the solution of the Schrödinger's equation should reduce to the solution to the functions that we already have seen, that is to the plane waves. Plane wave looks like this, exponential to the power I kr, where k is the quantum number, the wave number of the plane wave. It is a quantum number. And now let's say we start with this plane wave solution without the periodic potential. And now let's say you have some little knob which controls the strength of the periodic potential. And right now the setting of that knob is at the value 0. The periodic potential has the value 0. And now you are gradually increasing the amplitude of this periodic potential. Okay. It is reasonable to expect that that the plane wave solution will transform somehow, but it will not completely lose its plane wave character. So this wave vector k will still remain the quantum number that characterizes this solution. But in addition, a new quantum number will appear. So this plane wave will become modulated. The amplitude of the plane wave will become modulated. And the new quantum number will appear, which I call n. And for now, I call this quantum number the band index. So now notice that the plane wave solution does not have the periodicity of the crystal lattice, because if you increase the radius vector r by a translation vector d, then the plane wave gets multiplied by a factor exponential to the power I k dotted with the translation vector d. The plane wave solution does not have the periodicity of the crystal lattice, but the modulus squared of the plane wave does have the trivial periodicity of the crystal lattice, because modulus square of psi is just 1 over L cubed. So d independent of r. Now, so this part, the plane wave part, doesn't have the periodicity of the crystal lattice, but its modulus squared does. Now, this new function, which modulates the amplitude of the plane wave, it makes this amplitude like wiggle. It turns out to be a periodic function of the coordinate r, and it does have the periodicity of the crystal lattice, not its modulus squared, but this function un of r itself. And this is the main result of Bloch's theorem, the main statement of the Bloch's theorem. Now, of course, the wave vectors k they're quantized. They are not quite continuous, but they're quasi-continuous. So what I mean is, I'm just transferring the result from the discussion of plane waves in the absence of any potential. So same applies to the wave vector in the wave function, in the Bloch wave function. So you imagine the crystal to be a cube, L by L by L cube, with periodic boundary conditions. So you take the same L by L by L cube, and you kind of make copies everywhere, make copies which form like a huge filling the whole space with those L by L by L copies of the crystal, like filling the whole universe with the copies of this crystal. All right, so the periodic boundary conditions imply that the wave vector k, each component, x, y, and z component of the wave vector, must be quantized in units of 2 pi divided by L, where L is the side length of that cube, and Lx, lowercase lx, ly, lz are integer numbers. And in total, there are n possible values of the wave vector, because, as we have seen earlier, each band consists of n different electron states. So the wave vector labels the quantum states that belong to the same band. The band index n here that labels the periodic functions that modulate the amplitude of the plane wave in a particular band. So the band index labels bands. For each band, it is possible, again, I am not saying that it is easy, but it is possible to find how the energy depends on the wave vector, and you will have some curves. So these curves are obtained by performing this band calculation for silicon. And these calculations are performed routinely for all materials that are known. There are people who make careers doing these calculations. They know all the tricks of that trade. All right. Now, of course, associated with the momentum, with the wave vector, is the momentum of the electron. So it is the product of the wave vector with the reduced Planck's constant h bar. But in crystal, this is not called momentum. This is called quasi-momentum or crystal momentum. The thing is that it turns out that this momentum-like quantity of an electron in a crystal, the crystal momentum of the quasi-momentum, is not conserved. Well, it is conserved. Momentum is conserved, but momentum of electrons in crystal is conserved up to something called the reciprocal lattice vector multiplied with h bar, integer multiple of this reciprocal lattice vector. But for small values of momentum, well, this is a slightly more advanced topic in this course. For our purposes, we can treat the quasi-momentum, the crystal momentum of an electron, as a regular momentum. In this course, we will not have to apply this momentum conservation laws, but I just want you to be aware that the properties of this quasi-momentum of an electron in a crystal, they somewhat differ from the properties of the momentum of free electrons without the crystal. So this is, for this reason, it is called quasi-momentum, and the details can be found online in Wikipedia or in textbooks. I just want to make the statement, but without elaborating on it any further. All right, but we will treat quasi-momentum as a regular momentum. So I will use this quasi-momentum and momentum words interchangeably. I just want you to keep in mind that momentum of an electron in a crystal has a somewhat different behavior, somewhat different properties. All right. Now, let's discuss the band filling and conductivity. If you apply an electric field, this produces a force on electrons. That force tries to accelerate electrons in the direction opposite to the electric field because electrons are negatively charged. Acceleration means that the momentum of the electron changes. The velocity changes and the momentum of the electron changes. In other words, the electron tries to go into a different momentum state, quasi-momentum state, that belongs to the same band. But if all momentum states of a particular band are occupied by two electrons, spin up and spin down, then no electron can change momentum state in a band which is completely filled. A band has 2n electrons, n is the number of primitive cells, and it is completely filled. Pauli exclusion principle prevents electrons from changing their momentum state in response to an external electric field. This means that from the point of view of conductivity, completely filled bands do nothing. It is as if they didn't exist. It is as if those bands were completely empty. Of course, completely empty bands also do not contribute to the conductivity of the crystal because of a material, because they do not have electrons, they do not have the charge carriers. And neither do completely filled bands due to Pauli exclusion principle. It is only if a band is partly filled that its electrons produce electric current when an electric field is applied. And the materials in which the bands are partly filled are well known. These are metals, and and semi-metals, so-called semi-metals. These two diagrams show the band structure not of some particular metal or semi-metal. I just drew some random curves called the x-axis, the k-axis, the y-axis is the energy axis, and so this just represents, they are not real materials, but just the fantasy, my fantasy. So the energy momentum curves in different bands of a metal, let's say they look like something like this, some random curves. If a metal, the Fermi energy in a metal is somewhere in the middle of one of the bands, or one of its bands. And so the bands with energies below this band are completely filled. They do not contribute to the electric conductivity, but this band, the upper band, where the Fermi energy is somewhere in the middle, they do contribute to the electric conductivity because the electrons, there are empty states, and electrons can change their momentum state. There are empty states for electrons to occupy in response, or for electrons to go to in response to an external electric field. Now, metals are found in the left part of the periodic table. Okay, so starting from lithium with one valence electron and all the way to the right, approximately the left part of the periodic table. If a rule of thumb, if an outer shell of an atom, of a free atom, is partly filled, then that shell becomes a partly filled band. So that's very simple. Now, I said earlier that energy bands may overlap. And semi-metals are metal-like materials whose two energy bands overlap, and the Fermi energy belongs to both of these overlapping bands. And both of these bands contribute to the electric conductivity. So here are some examples of metals and some examples of semi-metals: bismuth, arsenic, stibium, antimony, alpha tin, and some compounds, tungsten, telluride, and so forth. By the way, in these compounds, the two bands, the bands do not overlap, but the band gap between the two bands is 0. Interesting in that respect. All right. Oh, just a reminder: Fermi energy is that special energy such that at absolute zero temperature, all states whose energies are below the Fermi energy are occupied, and all states whose energies are above the Fermi energy are empty. So Fermi energy at zero temperature separates the empty states from the occupied states. All right. Okay, so we have understood metals and semi-metals. Now let's move on to dielectrics and semiconductors. And so at absolute zero temperature, neither dielectrics nor semiconductors conduct electricity because the Fermi energy in both materials is in the middle of a band gap that separates one band which is completely filled, let's say this band, and the upper band which is empty at absolute zero temperature. While metals from the previous slide are characterized by metallic bonding, in which the valence electrons become shared by the whole crystal, the dielectrics and the semiconductors are characterized by the remaining three types of bonding that we have discussed earlier, namely ionic, van der Waals, and covalent bonding, with ionic bonding and van der Waals bonding being characteristic of insulators, of dielectrics. Now, with a little bit of like, there is some subtlety. So for example, whereas, okay, so and covalent bonding is can be characteristic for both insulators and semiconductors. Okay, I will return to the type of bonding and the two types of materials, but let me just tell you first that the difference between semiconductors and insulators or dielectrics is not qualitative, it is quantitative. It is just the size of the band gap. So loosely speaking, if the band gap exceeds 6 electron volts, then the material is an insulator. And if the band gap is below 6 electron volts, then the material is a semiconductor, even though this 6 electron volts is the boundary between the two types of materials is a little bit diffuse. So for example, diamond, the band gap of diamond is 5.5 electron volts, so close to 6. And sometimes it behaves like a dielectric and sometimes as a semiconductor. Examples of... All right, okay, so no, nothing comes to mind with the band gap close to 6 electron volts, but okay, diamond is a good example. All right. Now back to the bonding types. So I said that ionic crystals are predominantly dielectric, like table salt, sodium, potassium chlorine or sodium chlorine. But whereas covalent crystals can be either dielectric or semiconducting. But in semiconductors, you can have covalent bonding and some other type of bonding. So, for example, gallium arsenide, the bonding in gallium arsenide is partly covalent and partly ionic because gallium and arsenide, so an electron is transferred from one atom to another. So there is some ionic bonding there. All right. Now, van der Waals bonding. Van der Waals bonding is extremely weak. Van der Waals crystals can exist at very low temperatures. So examples of van der Waals crystals would be, of course, the noble gases, like argon, krypton, because the noble gases do not form chemical bonds because all of their shells are completely filled. But also van der Waals crystals. Solid ice, CO2, carbon dioxide crystallizes due to van der Waals forces. What else is there? Iodine also forms van der Waals crystals. I think CH4. All right, so van der Waals crystals is not something is not something exotic. It is not just the property of noble gases. So other substances can form such crystals. Now, van der Waals crystals are predominantly, all of them are insulators. You can say that, so for example, the only exception that comes to mind is graphite. So in graphite, you have layers of graphene layers, that carbon atoms forming this honeycomb structure. And those layers are, within each layer, the atoms are bound by covalent forces in the sp2 hybridized electrons, or sp2 hybridized orbitals, which form covalent bonds. But the layers themselves are bound together by weak van der Waals forces. So now the graphite is a semi-metal, but its conductivity depends on the direction in which you apply the electric field. So if the electric field is applied in those graphene planes, then conductivity is relatively high, but out of plane conductivity in the perpendicular direction is low. Why? Because the planes are bound by van der Waals forces. Okay, so this is all very interesting, but I guess I'm digressing a little bit, so let's move on. So now the main message of this slide is that the band gap, the Fermi energy in the semiconductors and the electrics is inside the band gap between two bands. The lower band is completely filled at absolute zero temperature. The upper band is empty. The difference between the two materials is the size of the band gap, which is of the order of electron volts, below 6 electron volts for semiconductors, and above, loosely speaking, 6 electron volts for dielectrics, even though this boundary value is diffuse. And the new piece of information is that because of this difference in the size of the band gap, even though at absolute zero temperature, neither semiconductors nor dielectrics conduct electricity, but at ordinary temperatures, like room temperature, 300 kelvins, 26 milli-electron volts, thermal energy is sufficient to promote a small part of electrons from the lower band, which would be completely filled at zero temperature, into the upper band, which becomes, which now has some electrons, and those electrons now become charge carriers. They can conduct electricity in semiconductors, and for this reason, in semiconductors, the band that would be completely filled at absolute zero, but now it loses some electrons, is called the valence band. Well, for an obvious reason, because of the valence electrons. It is formed by the valence electrons. And the upper band, which was empty at zero temperature, but which now has a small fraction of electrons at non-zero temperature, is called the conduction band, because it has electrons that conduct electricity. All right. Okay, so here is our valence band, and here is the conduction band. You can have two possibilities. The top of the valence band and the bottom of the conduction band may happen at the same value of the wave vector, or at the same value of the quasi-momentum of the electron. Such materials are called the direct bandgap semiconductors. Or the extrema of the valence and the conduction band may happen at different values of the wave vector or quasi-momentum, and such materials are called indirect bandgap semiconductors. The importance of this distinction between the direct and the indirect bandgap semiconductors is how the two types of materials interact with light. So the direct bandgap semiconductors are very active. They have high absorption coefficient, but the indirect bandgap semiconductors have much lower absorption coefficient, and also the radiative recombination, about which we will be talking in one of the future lectures, also proceeds much faster in direct bandgap semiconductors than in the indirect bandgap semiconductors. Examples of the direct bandgap semiconductors are gallium arsenide, which I have already mentioned, but also other materials like indium arsenide. Here they are. Indirect bandgap semiconductors are, of course, silicon, the most important semiconductor of all for our practical purposes, and germanium, aluminum arsenide, gallium phosphate. Good. Now we have two more slides. So electrons in semiconductors, conduction electrons, are there. They come into the conduction band from the valence band. So, and now conduction electrons can conduct, they respond to an external electric field, they conduct electricity, electric current. Now, the valence band now also has empty states, empty quasi-momentum states, because the valence band has given away some of its electrons to the conduction band. By the way, this fraction of the electrons from the valence band that go into the conduction band is very low. It can be, let's say, 1 part in a trillion, 10 to the negative 12. But If your valence band has, let's say, 10 to the power 25th electrons, then you take 1 trillionth of that, you will end up with 10 to the power 13th electrons in the conduction band, which is a non-negligible number. All right, so in the valence band, we also have empty states. Those empty states, this means that also the valence band now has empty states, and now the valence band is not exactly completely filled. So the valence band can also contribute to the electric current when you apply an electric field. However, in the valence band, now the exact description of the electric conductivity in the valence band would be still in terms of the electrons. Electrons are the true charge carriers, but the number of electrons in the valence band is huge. The number of empty states in the valence band is relatively small. It is much more convenient to describe conductivity of the valence band in terms of those empty states. Treat those empty states as positively charged particles, like holes. Like, imagine you have a tube filled with water, and inside the tube, you have air bubbles. Now you can describe the motion of the air bubbles in terms of the motion of, completely in terms of the motion of the water by solving some complicated hydrodynamic equations and thinking how the water flows, like in this geometry around those air bubbles. But this description is extremely complicated. Instead, you can just treat the air bubbles as particles, even though they are not real particles. Treat them as particles and see how they move. The buoyancy acts on them and all these things. So something similar happens with the empty states in the valence band, empty momentum states in the valence band. You can treat them as particles, and because those particles are not real, they exist only inside the material, they are called quasi-particles. Quasi means not really a particle, but something like a particle-like object. So in semiconductors, we have two types of charge carriers: negative electrons that live in the conduction band and positive holes that exist in the valence band. And why the holes are positive, this can be understood if we consider this picture. So let's say we have a silicon crystal. Some of the valence electrons in silicon get so the valence electrons in silicon form chemical bonds between the neighboring silicon atoms. But some of those valence electrons are detached from their host atoms and they are free to move in the crystal. And they leave an empty state behind. The region which a valence electron leaves behind when it gets detached from the atoms, is positively charged. This is a positively charged region. Now let's say you are applying an electric field. Electrons, free electrons, conduction electrons move against the electric field. Now, as for these positively charged regions, electrons from the neighboring atoms can hop and fill those empty states, empty spaces. And so the net result is that this positively charged region has displaced in the direction along the electric field. So it does behave as a positively charged particle. And so those positively charged particles are the holes. So we have two types of charge carriers: electrons that move against the electric field and positive holes that live near the top of the valence band, and which are the positive charge carriers moving along the electric field. With this, I would like to thank you for your attention. And next time we will begin the semiconductor part of this course. Goodbye.